Great. Yeah. Thanks everyone for coming back bright and early today. And by the way, I posted the slides for today already in the day 2 Slack if you want to follow along on your own devices. So I'll continue the discussion from yesterday morning, but there's been a lot of really interesting stuff since then. So let me just start with a quick review from what we did in the first 2 lectures yesterday. So as a reminder, gravitational waves from compact binary coalescences have this special property that they directly encode the luminosity distance to the merger. And that is why they're called standard sirens. And so the way that works is that the gravitational wave strain that is proportional to the chirp mass, the redshifted chirp mass of the binary, and decays inversely with the luminosity distance. So this redshifted chirp mass, which we can read off directly from the frequency f of t and the frequency derivative f dot, sets the intrinsic loudness of the gravitational wave signal. And then the way that it appears in our detectors, its amplitude in our detectors, then directly tells us the luminosity distance. And also we talked about how there's also this function of the angles. So like the inclination of the binary is degenerate with the distance in that way. And of course, the redshift of the source is completely degenerate with its mass because the frequencies are redshifted. And so the chirp mass that we measure is the redshifted chirp mass. So the true masses of the systems times 1 plus redshift. And then we also talked about the different ways that we can use gravitational wave distances and assign them to a redshift for the source. And that's how we can build our Hubble diagram or the redshift distance relation. So the 3 different categories of ways that we talked about getting that redshift information was bright sirens, where there's a counterpart, and that counterpart, especially if it's a kilonova or like an optical counterpart, like a AGN flare or something, tells us what the host galaxy is because we can localize it really well with our electromagnetic telescopes, unlike our gravitational wave observatories, which do not localize things well. In the absence of having a unique host galaxy, we talked about how you can marginalize over potential host galaxies in the gravitational wave localization, which is called dark or statistical sirens. And then we also talked just a little bit about spectral sirens, which I'll go into more detail about all of these today, but especially the spectral siren case, which we didn't spend too much time on yesterday. And that's when we use features in the source frame mass distribution to directly, in a gravitational wave only way, break the degeneracy between mass and redshift. And so we actually just use the redshifted mass versus distance to infer the source frame mass and the cosmology simultaneously. Okay, so today I just wanted to give you a sense of some more of the details that go into these measurements and also a lot of the active research in the field. And so to do that, we can dive a little bit more into the statistical framework. And we had great lectures going more into statistics stuff yesterday afternoon by Laurence. So I think this will fit in thematically pretty well with that. Right, so here's a graphical model, often also called like a directed acyclic graph or DAG, which illustrates the statistical framework that we used for the first standard siren measurement from the bright standard siren, the binary neutron star event GW170817. And so the way to read this model is like, these are all the variables that go into the problem. These are the data sets that we have access to. So XGW here is the gravitational wave data. VR is the measured recessional velocity of the host galaxy. And then this VP in brackets is a measurement of the peculiar velocity in the neighborhood of the host. So it's like a mean peculiar velocity of the host. And then these are underlying true parameters that we don't have direct access to. These are like the measurements that we have. These are parameters, physical parameters that we want to infer. So there's the distance to the gravitational wave source. It's technically the luminosity distance, but this event was so close by that it's essentially just a linear relationship. So it doesn't matter which distance you're talking about. So that's the distance. Then cosine inclination of the binary system. VP is the peculiar velocity of the specific host galaxy. So it's true peculiar velocity of host galaxy NGC 4993. And then H naught is the Hubble constant. And then these different arrows are telling you like which true parameters each piece of data depends on. So the gravitational wave data is only sensitive to the distance and the inclination of the source, but the distance is also affecting our measurement of the recessional velocity. And so that recessional velocity, right, depends on the distance to the source, the peculiar velocity, and the Hubble constant. If you have these three variables, you can directly solve for the recessional velocity, and the peculiar velocity that we measure, the mean peculiar velocity, is just informed by the true peculiar velocity. And all of these parameters up here are parameters that we need to put priors on in the inference, whereas this is the data. So we can actually just like expand out our likelihood and solve for the joint probability of our three data sets, the gravitational wave data, the measured recessional velocity of the host galaxy, and the mean peculiar velocity in the neighborhood of the host galaxy. And those depend on these true parameters that we talked about. And these data sets are all statistically independent of each other. So we can just expand this out. And this is exactly what we just said. That's informed by these true, so each data set is informed by these true parameters. Do you guys hear like a ringing noise?
Yeah. Yeah, I guess you can continue with try to.
Okay, it's like I didn't think my tinnitus was that bad. Okay. I can try moving the mic down.
Yeah, that also works, I guess.
I don't know where to put it.
It's a mic.
Oh,
Yeah. We could be talking with try to change things if it works.
goodness. Okay. Cool. Yeah, so this is just telling you like the right, the gravitational wave data depends on the distance and inclination, and we just multiply these different datas together because they're statistically independent using this graphical model. So the recessional velocity depends on distance, true peculiar velocity, and the Hubble constant, and then the mean peculiar velocity depends on the true peculiar velocity. So then this term here, the recessional velocity, is given by this. This is kind of an assumption we make for how that measurement of the recessional velocity depends on the distance, the peculiar velocity, and the Hubble constant. And we assume that it's normally distributed, so given by a Gaussian distribution around the true recessional velocity, which is going to be the peculiar velocity plus, and this is like a linear approximation because again, this is a very low distance, low redshift galaxy. So its true Hubble redshift is approximately just h naught times the distance, and then plus the peculiar velocity gives you like the true recessional velocity, but our measurement of that recessional velocity has some uncertainty to it, and that's given by this sigma squared, and that's the variance of the normal distribution, and we have a measurement of this sigma 72 kilometers per second. That accounts for just the uncertainty of virial motions within the galaxy group. So we took this measurement of the recessional velocity. This is the measured recessional velocity of the galaxy group containing NGC 4993, the host galaxy. And that's taken from the 2-mass survey. And there's a paper that like fits for the virial motions of the galaxies in that group. And so that's the recessional velocity of this particular host galaxy. And then similarly, we assume a Gaussian distribution or a normal distribution denoted by n for the measurement of the peculiar velocity, given the true peculiar velocity of this specific host galaxy. And so that has a mean of the true, centered on the true peculiar velocity with a variance sigma squared VP here, where this standard deviation is taken to be 150 kilometers per second. And that gives you the uncertainty in the peculiar velocity of that galaxy group. And it's actually pretty large. So our estimate of the recessional velocity from the system from the 2-mass survey is around 3,300 kilometers per second. And the estimate of the mean peculiar velocity in that neighborhood is 310 kilometers per second, which is a pretty large peculiar velocity. And that's just because the group that this galaxy in happens to be like moving towards the great attractor. And so usually, I mean, we've only had one example for gravitational waves, but like most galaxies don't have such a large peculiar flow. So yeah, that's pretty much how that works. This gives us our likelihood, and then by Bayes' theorem, we can infer all of these parameters with priors on these parameters. So we take the distance prior is like roughly uniform in co-moving volumes. The cosine inclination prior is flat. The peculiar velocity prior is flat. And for the h naught prior, we took a flat in log prior. Great. And so I guess, does anyone have any questions about the statistical framework? I don't know how much statistics people have seen. Yeah.
Is your H naught prior flat in long space?
Oh, for like no great reason. You can pick whatever prior you want on the Hubble constant, because like, especially when you have a lot of measurements, it doesn't matter. There are arguments that this is kind of a scale factor, in that the redshift is h naught times distance, and so like it makes that like for something that's kind of a scale factor, often you want to take something that's flat and the log of that parameter. But yeah, there's like, you can pick a flat prior on h naught. You can pick a prior, like the real Bayesian thing to do would be to pick a prior that's informed by your previous beliefs, in which case you might say, well, I think h naught is probably around 70, but then the likelihood might not be as informative compared to that prior. So yeah, it's like arbitrary.
If people in the back hear the question, could we have a mic on it?
Oh, sorry. The question was why did we pick a flat in log prior on h naught? Okay, great. So yeah, I'll go a bit more into some statistics later, but just some results from that paper because we also talked yesterday a bit about like this inclination distance degeneracy and how that is responsible for a lot of our uncertainty on the Hubble constant. So here's a plot from that first paper by the LIGO collaboration and like 20 other collaborations, which shows the joint distribution, the joint posterior on the cosine inclination and the Hubble constant. And so you can see there that gravitational wave posterior is in blue. And so there is this correlation here where this is due right to the fact that there's this degeneracy between inclination and distance. So cosine inclination of -1 here is like face off systems, and those correspond to the smallest distances, and therefore the smallest values of the Hubble constant. But there's this tail because we can't constrain the inclination that well towards more edge-on systems, which would be at higher distance, and therefore higher values of the Hubble constant for a fixed redshift. And so what this implies is that if you have an independent measurement of the inclination of the source, you can then get a tighter posterior on your Hubble constant for that event. And so there were a few papers that did this, but I think maybe the most recent one was this paper from 2019 by Hoto Kazaka et al., where they actually had really late observations in radio of the jet, that gamma ray burst jet that was associated with this event. And they observed superluminous motion and then used that to constrain basically the viewing angle of the jet and therefore the inclination of the system. And so here's the posterior that they get. So here for reference is the original gravitational wave posterior, and then using this modeling, these additional data sets and some modeling of the jet. So this is like a power law jet model. I'm not too familiar with the specifics of jet modeling, but basically they constrained the Hubble constant to be this tighter measurement. So that's ruling out things in the high H0 tail or these more like edge-on configurations here. But also kind of ruling some things out here. So it was like a little bit, the inclination was probably around like 30-ish degrees. So this is great because this really is a pretty dramatic improvement on the Hubble constant from this one event, which is the only bright siren we have so far. The problem with this is that one of the reasons that we want to use gravitational waves for doing this cosmography measurement is because gravitational waves are have different systematics than other ways of getting the Hubble constant, but also, especially in this bright siren way, they have very little systematics. Like the main systematic is really just the calibration of our detector. We like directly measure the distance to the source, right? There's no distance ladder, there's no like additional astrophysical calibrations. One of the appeals of doing this is that it's very clean. And then once you then try to make a tighter measurement by introducing additional astrophysical modeling, you're introducing possibly additional systematics, as you do with anytime you introduce a new model, we don't know anything perfectly. And so that's illustrated here. It doesn't seem to have a huge effect, but like different ways of modeling the jet and modeling that electromagnetic data can give you slightly different posteriors on your Hubble constant because you just infer like a slightly different inclination. So that's something to keep in mind. Okay, so yeah, we also then going back to the dark siren method and some of the additional details that go in there, and I think there were already some questions yesterday about some of this. But when we don't have a unique host galaxy, we then use a galaxy catalog to marginalize over the possible hosts. And there are several complications that we have to deal with when we do that, when we bring in a galaxy catalog. The first one, which we talked a bit about yesterday, is that, okay, so you have a host galaxy and maybe any galaxy, or you have a galaxy catalog and any galaxy in that catalog could be the host, but probably not all galaxies are equally likely to host a gravitational wave merger, right? Some galaxies are like dinky little dwarfs, and some galaxies are like huge and have so much stuff in them. And so it's not that like every galaxy is going to have the same number, the same rate of gravitational wave mergers per galaxy. So we have to choose weights when we do this marginalization that are proportional to the hosting probability. We want to weight some galaxies more than others if we think they're more likely to host the gravitational wave merger. And so this is from the paper that I showed yesterday, where we did this kind of toy exercise for GW 170817. And because this event is really well localized, it doesn't end up making a huge difference because you really only have like one group of galaxies in the gravitational wave localization. But you can see here, these are, one way to think about where the information is coming from is by looking at the redshift probability that you infer for like where you think the gravitational wave merger is coming from in redshift space based on where the galaxies live in redshift space, divided by if you just had a completely random distribution of galaxies, which would follow this like p volume term. And so if you just had like so many galaxies, like infinitely dense galaxies, and they were completely randomly distributed in volume, this would be completely flat and you would never have any information about what your Hubble constant is. But the fact that there are like some peaks in here is what gives you the informative measurement. And these are just showing like different luminosity thresholds and also different ways of like weighting your galaxies according to like B band luminosity or weights proportional to K band luminosity. So you can see that it does make slightly of a difference. For example, there seems to be this like little galaxy here, or like a few galaxies at slightly lower redshifts that are very bright in the B band. And so there's some additional support down here when you like have those B band luminosity weights. And then this is the effect that it makes on your resulting Hubble constant posterior. Was there a question? Oh, yeah.
Yeah, so in your gravitational wave telescope aperture, if you have a galaxy catalog there, supposing that the mergers are coming from the high mass end of this like stellar theory, can you use information on like star formation rate and specific star formation rate of those galaxies to sort of guess, okay, well, I'm guessing the neutron stars are being made in these ones and so on?
Yeah, that's a really great question. So yes, you can definitely do that. And so I should say you want to do it both for this sort of measurement, but also if you're like trying to follow up a galaxy catalog and like see, you want to find a counterpart. And so a lot of people and like some of the teams that first found the counterpart to GW 170817, they have a galaxy catalog and they want to like rank which galaxies to point their telescope at first. And so you can definitely use theoretical predictions for like, I think, and the way this usually works is that the progenitors to these black holes or neutron stars that we're observing are stars. They might be very massive stars. we think they are probably low metallicity stars, and so that can play into it. And then you have some distribution of delay times between when you think the stars formed and then the black holes or neutron stars merged with one another. And so you can do the full modeling. And so this is, so like the B band and K band weights are like a very simple way of doing that, where like B band luminosity, it's like blue galaxies, so it's roughly the proportional to the star formation rate, whereas the K band is like more reddish galaxies, so that's roughly proportional to the stellar mass. And so that's kind of like the two things we use. We think it's some combination of star formation rate for like short delay times and stellar mass for long delay times, but you can definitely do like a more sophisticated thing, and people are working on it. And for people who are like, we do this for other transients all the time too, right? Like for gamma ray bursts and fast radio bursts, and like every transient studying the host galaxies is very interesting astrophysically also. But yeah, great question. So, okay, the other detail we want to worry about or think about when we're doing this galaxy catalog statistical dark siren approach is the incompleteness of the galaxies, the catalog, because not every galaxy is going to be included in pretty much any catalog. So galaxy catalogs are incomplete, and we have to characterize and account for this. And so this is again from this one paper that I'm just focused on, where this shows the completeness fraction as a function of redshift of this GLADE galaxy catalog, which we used in the analysis. And this shows the completeness for galaxies down to these different luminosities. So if you if you have a relatively high luminosity threshold where you only care about galaxies that are brighter than 0.25 L star in the B band, then you're going to have you're going to be pretty complete. And this redshift range, these are really, really low redshifts, right? That's because this event was very close by. So that gives us the redshift range we care about. But yeah, then you can see at higher redshifts, we're usually more incomplete because catalogs tend to be magnitude limited. But then if you go down to a lower threshold, you start to miss more galaxies. Even at like redshift 0.01, which is where we think this event was, you only have like 50% of the galaxies that you think should be in the universe. Only 50% of them are actually in your catalog. So you have to do something about the missing galaxies. Otherwise, you're obviously going to get a bias if you just assume, oh, there are no galaxies over here, and my gravitational wave couldn't have come from over here because there are no galaxies in the catalog. That's going to bias you. And then another aspect that we worry about are, okay, the examples I've been showing you, the GLADE catalog is this compilation of galaxy catalogs that all have spectroscopic redshifts. So we have a spectrum for each galaxy, and that gives us the redshift. There's a lot more galaxy catalogs that only have photometry information for every galaxy. And there's this whole research area about how to assign redshifts just from photometric information. These are called photometric redshifts, and probably a lot of you deal with photometric redshifts or work on photometric redshifts because this is a really hard and important problem. But the statistical dark siren approach with gravitational waves is a slightly different application of like photometric redshifts than a lot of other applications that people develop photometric redshifts for. And so we have to properly model the uncertainty in the galaxy redshifts in a way that doesn't introduce a bias in this case. So this is just a series of plots from this paper by Baum et al., where they were looking at photometric redshift specifically to try to analyze one of our very well localized binary black hole events. I think it was GW190814. So like a really well localized event, but it was probably a binary black hole merger and probably like wouldn't have had an electromagnetic counterpart. So they had to use these galaxy catalogs, and these are a few different galaxy catalogs. And this shows the average difference, kind of like an average bias between the photometric redshift and the spectroscopic redshift as a function of the photometric redshifts. So you want this number to be as close to 0 as possible. So this seems pretty good. You also want, this is like a measure of the intrinsic scatter in the bias at each redshift bin. And so you also want this to be pretty small. And then this is like an outlier fraction. So in cases where like your photometric redshift assignment is very much different from the spectroscopic redshift. And you also want this to be small. So anyway, there's this whole way in which we want to incorporate like the best photometric catalog information and make sure that biases in photometric redshift estimation aren't then translating to biases on the gravitational wave Hubble measurement. Okay, then the next thing I wanted to talk about leading us into the spectral sirens is really like how we do population analysis. And this is crucial to like a lot of, you know, cosmology and astrophysics, is combining information from many events. And in gravitational waves, we often do this population analysis in the hierarchical Bayesian context. So I'll just give like a super quick introduction to hierarchical Bayesian inference. And the way to think about this, the way that I often think about it, is starting with how we analyze a single event in Bayesian statistics. And so, right, we saw a similar equation yesterday with slightly different notations on one of the slides. And so this is the posterior on our true parameters for our event I, given the data for that event. And that is equal to our likelihood times our prior divided by the evidence. When we're analyzing a single event, then normally we just like pick, you know, whatever prior we want. And then we often don't really care about this evidence or this marginal likelihood. It's just a normalization factor. But we can always get this, right? So it's a normalization factor that just ensures that our posterior integrates to 1. So it's really just the integral of the stuff on the top. So if we really wanted our evidence for this model H, we could do this integral. The way that I often think about doing a population analysis is you just want to find the best prior to use for individual events. And so you just want to find like the underlying distribution that those thetas are drawn from. And those thetas could be like the distances of your gravitational wave events, the masses of your gravitational wave events. So there's like some mass distribution of binary black holes that we want to infer. And that's telling us, okay, when we see a gravitational wave, a new gravitational wave event, we now have a prior that we should use when we infer its masses because we know what the mass distribution of black holes is. And so instead of just having some prior that we just pick out of the hat to use for our individual event inference, we consider a family of priors, and that's just our population model. And so we can just introduce some set of parameters, lambda, which are going to give us these possible range of distributions for our population model. So in the case of like a mass distribution, this lambda could be, you know, if we fit a power law, it could be the slope of the power law. And so Now what we care about is the likelihood given our population model and these lambda parameters, which we often call the hyperparameters. And this is really just like if in the absence of selection effects, this is just the evidence that we had on the previous slides. For each event, we just like multiply together the evidences. So this thing on the top is basically the same as the evidence that we had down here. And we just multiply that together for all of our events I, because assuming each piece of data from every event is statistically independent. And then the only thing we include is this denominator term down here for every event. We also include this selection effects term, which is the fraction of detectable systems in the population. And what this does is it basically accounts for the fact that some true parameters produce data that are easier to detect than others. So like in the gravitational wave context, masses that are higher are easier to detect. And so we want to infer the underlying astrophysical distribution, not the detected distribution. So we include this selection effects term. And I'm going through this like really quickly. There's a lot of derivations on this. You can check out these papers to see like where this hierarchical Bayesian likelihood with selection effects comes from. And so the connection to cosmology is that when we do a cosmological analysis, it actually is a population inference because our H of Z, which we're trying to infer, is common to all events. So this lambda, this set of hyperparameters includes things like the Hubble constant and omega matter and anything else that is setting your parametrization of H of Z. And so we have to use this hierarchical Bayesian likelihood. And the thing I just wanted to point out is that both in our population model and in the selection effects, cosmology is correlated with the mass distribution of our binary black holes and the distance distribution of binary black holes and neutron stars. And so this enters in because our source frame masses that we infer are always degenerate with our cosmological assumptions because we're inferring redshifted masses, first of all. And so that's always going to be correlated, like the redshift, when we infer the source frame mass distribution, we always have to assume or marginalize over some assumptions about H of Z. And then also in the selection effects, this induces a correlation between mass and distance. And we can see this simply if we just look at all of our detected events in distance versus mass. And so we can detect more massive things to higher distance generally. And so that's why when you look at the furthest away gravitational wave events that we've detected, they necessarily have to have this higher mass. So selection effects induces this correlation, even if there's no correlation in the underlying astrophysical distribution. Okay, and then, yeah, so I'll just say that, so this is actually the whole point of spectral siren cosmology. We use these correlations between source frame mass and distance, between cosmology and source frame mass and distance to explicitly measure cosmology using the mass distribution. And if you ignore information from the population distribution or any of the other prior or modeling choices of the parameters you're marginalizing over in your inference, that can lead to systematics or bias. So you really do have to do everything all at once. And I think maybe we can take our break now, since it's been like 40 minutes, and then I can go into some more detail about how we do the spectral siren inference, and some other stuff. So yeah, let's take a 10-minute break.
Okay.
Cool.